Okay, welcome back. Let's look at an example on this Doppler effect. And the example comes straight from the book. It says, a police siren has a frequency of 550 hertz. As the police car approaches you, 450 hertz after it has passed you, the police has a frequency 550 hertz as the police car approaches you. And if it goes away from you, and it is receding, they say you observe 450 hertz. And then, so how fast is the police car going? So let's erase the board and try to figure it out. So you're not moving. So I will just go to this formula here. So only the police car is moving. So we get only this. The observer has zero speed. V observer is equal to 0. So we get f prime will equal to just, this is 1 plus 0, it's 1. So you just get f over 1 plus or minus v source over the speed of sound, like so. Now, here you are. You're not moving. V observer is equal to 0. You're not moving. When the police car is moving towards you, V source, we don't know what it is. You hear f prime equal to 550 hertz. And so we get this. F prime, when it's approaching you, let me call it, when it's approaching you, let's see. If it's approaching you, it's trying to make the fraction larger. And so a smaller denominator makes an overall larger fraction, so we will go with the minus sign. When it's approaching you, I'll put it minus sign. You have f divided by 1 minus vs divided by v, like so. And then we know this. This is 550, they told us. This is 550. And then when it's going away from you, v plus, when it's going away from you, so you're still here, and the police car has passed you. So now it's going away from you. Vs. It's at some speed. It's still the same speed. When it's approaching you, it's something, and when it's going away from you, we call this one f minus. I'm going to call this f plus, and it is 450 hertz. Okay. So you got 450 equals to f over 1 plus Vs over V. V is 343. And the question is, find V. Okay, find V. We can, the frequency with which the sound is emitted, F here, it's a certain frequency. Let's say if the police is not moving, it's a certain frequency. Let's say maybe it's 500, I don't know. It's a certain frequency. So we will write this one as follows. We'll write F, therefore will equal to F minus, I'll call it F minus. F minus, I would drop the prime. F minus, and it is just 1 minus Vs over V. And then here you get F will equal to F plus, and then you have 1 plus Vs over V. And we have to solve this. If we divide the two equations over each other, we will just get this over this will equal to 1. So let's see how that works. Might be faster way, but let me just divide them. So 1 will equal to F minus times 1 plus Vs over V over F plus times 1, F minus would go with the minus sign, 1 plus Vs over V. So there is some algebra here. I will multiply both sides by F plus over F minus to get F plus over F minus will equal to 1 minus Vs over V over 1 plus Vs over V. let's multiply both sides by just v, by v over v. Let's see here. Yeah, I mean, we have to solve for Vs in a way, and somehow we have to solve for Vs. Okay. So let me just, if this divided by this are equal to 1, then this has to equal to this. Yeah, maybe that's quicker. That's quicker. I should have done it earlier. There is a formula at the end. That's why I'm not really interested in it. But let's just write it. I get F plus times 1 plus Vs over V. I trust you all can do this algebra here. Minus 1 minus Vs over V. Let's just multiply. So I get F plus, and then F Vs over V times F plus will equal to F minus times 1 is F minus, and then F minus times negative that will be negative Vs over Vf minus. Let's move this to this side and this to the other side. So we get this, we have Vs over V F plus plus Vs over V F minus will equal to F minus minus F plus, and we will factor Vs over V on both here, so we get F plus F plus plus F minus times Vs over V will equal to F minus plus F minus minus F plus. Divide both sides by this, so you get Vs over V will equal to F minus minus F plus divided by F. I'll put F minus plus F plus, F minus plus F plus. Same thing, F plus plus F minus, or F minus plus F plus. Same thing. And then multiply both sides by V, so that V goes away. And you get this. So let's try to calculate it. F minus is 550. Minus F plus, that's 450. F minus is, again, 550. But now plus F plus, which is 450, times the speed of sound, which is 343. And you get what? This will be 100. And this is 1,000. So 100 over 1,000 is a tenth, times 343, so that's 34.3. And I hope I have it right after all this work. So let me just double check my, yeah, it's 34.3. 34.3. I mean, so from now on, if you're given the frequency when it's approaching, the frequency when it's receding, you can simply use this formula without going through all the algebra I went through. It's a formula. It's like here you solve for f prime in terms of the Vs and Vo, but this one is kind of, we're inverting it. We're solving for the Vs in terms of the f primes. So that's that. In the book, they also discuss the Doppler effect as it applies to light waves or electromagnetic waves. I'm not going to discuss that because, I mean, even the book too, they say you need special relativity to derive the formula. So we're not going to discuss it. I will just hold it for Physics 231 to do that. So they have a formula for it. All you need to just be aware of, if let's say a light source is moving away, then it will, we call it a redshift, because if it's moving away, it will, the frequency will become lower, so the wavelength become longer, so that's toward the red. Or the blue shift, if it's going towards you, the frequency will be higher, which is the blue. The colors as toward the red, it will be longer wavelengths or lower frequencies, and toward the blue, it will be higher frequencies or shorter wavelengths. Okay, so now I'd like to do some example problems from the end of the chapter. So let me erase the board and write down the problem. All right, so in this problem from the end of the chapter, it says bio, so it applies to biology. A bat locates insects by emitting ultrasonic chirps and then listens to the echoes from the bugs. Suppose a bat chirp has frequency of 25 kilohertz. How fast would the bat have to fly, and in what direction, for you to just barely hear the chirp at 20 kilohertz? So remember, the frequencies that we hear are between 20 hertz and 20,000 hertz. So this is problem number 43, by the way. Number 43 from chapter 14. I'm sorry, chapter 16. So from homework 14, chapter 16. So so here you are, let's say, here you are, and the bat emits waves. If the bat is stationary, then it will emit at frequency of 25 kilohertz. So these are not audible to us because we can hear between 20 to 20 kilohertz, 20 to 20,000. So for us to be able to hear it, the bat has to be moving. What do you think? The bat will be moving away toward, or maybe away from us? What do you think? Well, remember, if the source, so you're stationary, the source is moving, then we have f prime will equal to 1 over 1, either plus or minus the speed of the source divided by the speed of sound, and then times the frequency. This is the frequency if it's not moving at all. So we would like this, instead of 25,000, we would like it to be just 20,000. So do you think I will use the plus sign or the minus sign? Notice if the frequency, if f prime is lower, then, so I want f prime to equal to 20 kilohertz. So it means the bat will be moving away from you to make the frequency lower. Moving away from you, it means a lower frequency means you take this frequency and divide it by a number that's slightly more than 1. So this number, we have to use the plus sign. So I will use the plus sign. So we have, on the left side, we have 20 kilohertz, divided by, so f prime over f divided by 25 kilohertz. So the kilohertz just goes away. Equals to 1 over 1 plus the speed of this source, the bat, divided by v, speed of sound. So I have 20 over 20,000, we just invert both sides. So I have 25 over 20, and 25 over 20 would be 5 over 4, or 1.25, equals to 1 plus Vs over V. Take the 1 to the other side, so you have 0.25 equals to Vs over V. So the bat will be going at a quarter of the speed of sound, which is about approximately 85.8 meters per second. So 0.25 times 343. Let me get my calculator here. 0.25 times 343. That's 85.75. 86 meters per 86 meters per second. Okay, so that's that first one. Okay, let me go to the next problem here. So the next problem has to do with ropes. It says you have a figure here, you have two strings, and it's problem number 47. So let me erase the board here. Number 47, or two ropes. Let's just erase. Just erase the whole thing. Number 47. So you have string 1 has a linear density 2 grams per meter. So mu1 is 2 grams per meter. We have the following situation. So here is rope tightened here. So you have string 1, looks like this, and then it is tied to a rope that is thicker. That's string 2, right? Just two ropes tied together. This is 1 and this is 2. So this is mu1 and this is mu2, right? And then rope 2 has a linear density, mu2 equals to 4 grams per meter. Now the tension, and this one here has length L1, and this one here is length L2. As you might expect, the tension will be the same throughout, right? It has to be the same, otherwise the ropes would have to move left to right. So, it says here, a student sends a pulse in both directions by quickly pulling up on the nut. So the student will pull here and then sends a pulse. The pulse will go this way and will go this way. So it will travel right and then travel left. It will travel right, it will have a certain speed, and it will travel left, it will have a certain speed. And remember the speed, let me call it V1, the speed 1, will be the square root of tension 1 divided by mu1. Since the tension is the same, it will just be tension over mu1. That's V1. And let me just separate it as the square root of tension divided by the square root of mu1. Similarly, V2 will be the square root T2 divided by mu2 square root. But T2 and T1, it's along the same. So the tension is the same, divided by mu2. So you will have the square root of the tension divided by mu2 under the square root. So those are the speeds. Now it says, what should the lengths L1 and L2, what is the relationship between them if it will reach, if the pulse that's released from here to here, it will travel the same distance as from, going from here to here will take the same amount of time as going from here to here. Well, we know that the speed V1 is this, V1 will be the distance traveled over time, so it's L1 divided by T, and so T will equal to L1 over V1, and then for V2, we wanted to travel a distance L2 within the same amount, T, and therefore T will equal to L2 divided by V2, and since we would like the time to be the same, by the time it has reached the right end or the left end, both pulses have traveled that same distance, so the time will be the same. And so so L1 over V1 will equal to L2 over V2. So L1 over V1, which I will write here, L1 over V1 will equal to L2 over V2. And so, let's see. So we have L1 over V1. But V1 is the square root of mu, is square root of T over the square root of mu, but we're dividing by it, so it will be the square root of mu1 divided by the square root of T. And then L2 over V2, so it will be L2 times, we're dividing by V2, so it will be the square root of mu2 over the square root of T. Square root of mu2 over the square root of T. Since the tension is the same, that cancels. And I think they want L1 as a multiple of L2, so L1 will equal to L2 times mu2 divided by mu1. And so we get L1 will equal to L2 times square root of mu2 over mu1. Mu2 is 4 and mu1 is 2. The grams per meter will cancel, so I get 4 over 2. And so it will be radical 2 times L2. So L1 will be a little bit longer, which makes sense because L1, it's less thick, so it's less kind of damp. The waves will travel quicker, and this one is more dense and thicker, So the waves will travel slower, those transverse waves. Okay, so that's that. All right, so that's good. Let's look at the next question here, which says a helium, it's number 50, a helium neon laser beam has a wavelength in air of 633 nanometers, and it takes 1.38 nanoseconds for the light to travel through a 30 centimeter of N-noun liquid. And then it says, what is the wavelength of the laser in this liquid? Okay, well, let's see. We need to erase this and then write it down. So let me erase this and then write down this question. So a laser emits light, electromagnetic waves. And electromagnetic waves, they travel at the speed of light in vacuum. This is number 50. So here is the laser, and it's traveling through a medium. So we were given lambda in vacuum is 633 nanometers, which is, by the way, nanometer means times 10 to the minus 9. So this is 6.33 times 10 to the minus 7. 633 times 10 to the minus 9 is 6.33 times 10 to the minus 7 meters. That's the wavelength. And the speed of light is in vacuum is 3 times 10 to the 8 meters per second. The speed of light in a medium will equal to the speed of light in a medium of index of refraction n will be the speed of light in vacuum divided by n, and n is the index of refraction. And in our case, we actually don't know the index of refraction of this medium. They're saying a pulse will travel, so this is the medium, whatever it is. So let's say there is a medium here. You send a pulse, so the light is in this is the laser pulse. This is vacuum or air, and here it is air. So, but it travels from here to here, this distance here. The distance is 30 centimeters or 0.3 meters, and it does that within a time of 1.38 nanoseconds. 1.38 nanoseconds, which is 1.38 times 10 to the minus 9 seconds. So what's the speed of light within this medium? Well, the speed will be just distance traveled over time, and it will be, so v will be the distance over time. The distance is 0.3, and the time is the 1.38 times 10 to the minus 9. So we get, let's write it down. So 0.3 over 1.38, and then times 10 to the minus 9. So that would be 2.17 times 10 to the 8 meters per second. Let's figure out the index of refraction. Index of refraction of this light. Of this medium here. The index of refraction. We have c over n is v, so c over v will be n. And will be c over v, and that's 3 times 10 to the 8 divided by 2.17 times 10 to the 8 cancels. And let's check out the calculator here. Put here minus 1. Times 3. I get about 2.17. So 3 over 2.17. So 3 over 2.17. That gives me 1.38. 1.38. That's the index of refraction. I remember we said the frequency when the light outside and inside, the frequency doesn't change. However, the wavelength changes. The wavelength inside this medium, let's call it lambda n, will be the wavelength in vacuum divided by n. That's also in the book. And it's just 633 nanometers divided by 1.38. 633 nanometers divided by 1.38. So it would be a slightly shorter wavelength in this medium, and it would be 459 nanometers. Okay, so that's that. And I would like to maybe do one more question. One more problem. So just for general waves, I would like to do a problem here, which is number 13 actually. So I'm going backwards a little bit. We didn't do any of those, so let me just remind you. So number 13. You have this wave that has that depends on x and t, and it's given by the following formula: 3.5 centimeters times the sine of 2.7x minus 124t. The first question says, remember the general form for a wave for x and t will be the amplitude times the sine of kx minus omega t. This is a wave traveling to the right. And remember that omega is 2 pi f and k is 2 pi over the wavelength. This is called the wave number. This is the angular frequency. So the first question, what is the amplitude? Well, the amplitude is what's in front, so that's 3.5 centimeters. In this case, k will be 2.7x, and they're telling me that x is in meters and t is in seconds. So k is 2.7. Omega will be what's in front of t, so that's 124. K would be in 2 pi over lambda here. Lambda is in meters, so K will be in 1 over meters. Those are the units. And omega would be in radians per second. I think they want the following. They want the wavelength, the frequency, the wavelength, and the speed. Okay, so the wavelength, lambda, will be 2 pi over K. 2 pi over K, so that's 2 pi divided by K, and K is 2.7. And we get about 2.33 meters. The frequency will be what? Frequency will be omega over 2 pi. Be omega over 2 pi, and that gives what? 124 divided by 2 pi, and that is about 19.7 hertz. And I think that's all they want. Oh, the speed. The speed is omega over k or lambda times f, whichever you like. Because what is omega over k? Let's see. Omega over k. Omega is 2 pi f divided by k, but k is 2 pi over lambda. So lambda goes upstairs. So you get 2 pi f times lambda divided by 2 pi. So that cancels, which is lambda times f. So either way will be 124 over 2.7 over 2.7, or if you like 19.7 times 2.33 will give you the same answer. So that's 46, about 46 meters per second. Okay. And this brings me to the end of this chapter, and our very last chapter will be next time, and it is about interference of waves, and we will talk about standing waves and so on, so superposition of waves. Okay, I'll see you next time.